I'll start slowly while you introducing. So good afternoon, everyone. Today we have a special session of the HPHIL Seminar because it is actually a joint organization with the Center of Classical Studies. Luckily, Professor Bernard Motte contacted us in order to have Professor Paolo Mancosu here to talk on a topic of history of philosophy, and we were really glad to be able to welcome a huge name of philosophy of mathematics in our seminar. So Paolo Mancosu is a professor at Berkeley University. He has published many books. His interests lie mostly in the philosophy of mathematics and its history, in philosophy of logic, and in mathematical logic. His written work is currently focused on neologicism, the philosophy of mathematical practice, and mathematical infinity. He has published many papers and many books, but I would refer to one published this year by Oxford University Press, and is somehow related to today's presentation, which is called The Wilderness of the Infinite, Robert Grosseteste, William of Auvergne, and Mathematical Infinity in the 13th century. Professor, we are really happy to have you here, and we are very much looking forward to listening to your presentation.
Thank you. Thank you very much for this generous introduction. It's great to be here. Nice to see so many people interested on I thought maybe it's the air conditioning. It's so hot today. Okay, so this talk is a mixture of history of medieval philosophy and contemporary philosophy of mathematics. In fact, there will be some mathematics. I'm not expecting you to be necessarily au fait with the mathematics, and in fact my attempt will be just to give you an idea of the contemporary mathematics that I bring to bear on some of these issues that we will discuss. But I'm going to start by giving you a context for what is going on here. So the history and philosophy of infinity is undergoing a significant historiographical mutation. As a consequence of the development of the theory of numerosities in the early 2000s, and this is the mathematical theory I will tell you something more about towards the end, new rigorous mathematical theories of counting at infinity have become available, and their very existence has served as a spur to question positions that were becoming ossified on account of a lack of available alternatives. Through the theory of numerosities, it has become possible to take a fresh look at the Cantorian paradigm. Cantor, of course, is the big name who puts the theory of infinity on a solid footing in set theory. And its very success, in a way, is the reason for why it was so difficult to think outside of that Cantorian box. That has dominated reflection on the history and the philosophy of the infinite. Now, at the same time, this work has brought a renewed interest on medieval and early modern authors who countenance the actual infinite in ways that challenge the dominant finitistic paradigm that was typical of Greek and of most Islamic and Jewish philosophy and mathematics up to the 11th century. On Tuesday, I gave a seminar in the Department of Classics where we went through the sources from Alexander of Aphrodisias to Ibn Qurra, who's the first author to question the consensus that one finds in the Aristotelian commentators that infinity does not admit of increase or decrease. Basically, there is only one infinite. Ibn Qurra is the first one who says, "What is that so?" and provides a counter argument to that position. So I've especially devoted attention, among others, to Ibn Qurra, the only infinitary thinker in the Islamic Middle Ages, to William of Auvergne, in the 13th century, and Robert Grosseteste, who's the author, and we're going to talk about him a lot, of the first attempts at computing with infinite numbers. And then there are later interesting personalities like Maignan, who writes in the 17th century, who's completely unknown, basically, except for a couple of articles written on him. But he has a treatise called De Infinito, which is an amazing piece of work, quite original, and so certainly worth famous. I wrote something about him, but there is space for more work. Okay, so my focus in this lecture is a combination, as I said, of medieval philosophy and recent theories of numerosities, and their connections to what is called measure theory, which is an area of analysis that I will tell you something about. So we begin by focusing on Robert Grosseteste. He's an Oxford theologian, first Chancellor of the University of Oxford, and then later Bishop of Lincoln. Incredibly important for the reception of Aristotle in the Latin Middle Ages, because he's the first who writes a commentary on the posterior analytics, and arguably the first to write a commentary on the physics, arguably because these comments on the physics were basically notes that he left in his book on the physics with the clear intent of writing a commentary, and then they were left at the Franciscan school in Oxford, and some of his disciples then later made this material known to other people. So what I'm going to look at is some of the part-whole intuitions that he defends concerning the counting of points in line segments in geometry. And then we will look at the substantive objection, which was already raised in the 13th century, and I can't underline enough how incredible this exchange is. And I'll tell you more about this, aimed at showing the impossibility of the idea that the number of points in segments, of different segments, co-vary with their lengths. So really, this is the idea that I'm going to pursue throughout the lecture. The idea that, and it's very intuitive, you must have been ruined by your mathematics courses not to see how intuitive and persuasive that is. If I have a segment which is 2 inches long, it's got all its points. The number of those points is twice as many as the number of points in a segment which is 1 inch long. Right? Of course, we'll see that from the point of view of contemporary Cantorian set theory, this is a non-starter. But the intuition is, I think, very powerful, and I think it's one of the most basic intuitions we have about measure and counting. So the key idea is that we're going to see that Grosseteste postulates that there is a way to have this covariation. Length corresponds to number of points in this kind of a way so that they covary together. And finally, I will ask whether this intuition can be given a proper mathematical treatment. But before we get started, let me also mention the broader significance of some of the material that we're looking at. Within the span of 20 years, from 1220 to 1240, Grosseteste and William of Auvergne, Bishop of Paris, presented very original views on the possibility of comparing infinites. It is tantalizing that the emergence of the discussion on different sides of infinity in Robert and William, which has been largely ignored in the literature, parallels a similar sudden shift, well studied by historians of theology, that took place approximately in the same period in theological debates concerning whether God's essence is infinite. Again, not being an historian of theology, to me this was a very surprising discovery, because, I was trained at the Catholic University of Milan, so I did actually quite a bit of theology and history of medieval philosophy, but, the first thing you think, if somebody says, so what do you think are the main, features of, properties of God? Well, infinity is one of the first that comes up, right, as well, it turns out that during this period, there are still debates about whether God's essence is finite. Whether God is finite, and that's a rather surprising thing. And how does it come about that this debate explodes in the early 13th century? It has to do with a kind of vision that the blessed have of God. How can a finite being, even if blessed, right, they're still finite beings, can have access to the infinity of God in this vision that they get of God? And so that's where infinity comes from in the theological debate as a very substantial issue. Okay, now we'll move to Robert Grosseteste. Now, James McEvoy, who's one of the great scholars on Grosseteste, says, speaking of his work, I do not know of any other work of the same character dating from medieval times, and I regard it as the original creation of a bold and powerful mind that had arrived at fullest maturity. What he's referring to here is this treatise On Light, written around 1225. On Light is at the very beginning of what is called the metaphysics of light in this period, and it's a cosmological treatise. It's an incredibly innovative cosmological treatise. Some 20th century physicists and cosmologists have gotten really excited about it because it has similarities with the Big Bang theory. The cosmos originates from the unfolding or multiplication of a point of light. So this picture has at least has been very suggestive for several people. But McEvoy surely intended to include in this originality Grosseteste's reflection on unequal infinites. And he wrote, likewise, his argument invoking mathematical infinity and relative infinities seems to have been his own invention, at least so far as our present knowledge goes. And in fact, having worked so much in this area right now, I can confirm that Grosseteste's originality has not been questioned here. On the contrary, I think that the work I've been doing brings out even more the originality of his thinking in this area, because we'll see that these ideas on infinity may seem rather non-standard with respect to our best theories of the infinite, or at least the theories that we have received as the best ones. They have been basically ignored by most people as being kind of, confused or unclear and so on. So Grosseteste discussed issues pertaining to mathematical infinity in On Light, which was written in the 1220s, but he also refers to that treatise in some passages of his commentary on the physics. So the commentary on the physics is not translated, and On Light is, there is a good edition by Cecilia Panti, but the commentary on the physics we only have in an edition in Latin, which is not great. And that's the Dales edition from 1963. Now, there are two contexts in which Grosseteste speaks of mathematical infinity. First of all, it discusses infinite numbers, which he thinks can be obtained by summations, infinite summations of what we would call divergent series. And this is the kind of stuff you can look at in analysis. There are series that diverge, they have no convergence point. But Grosseteste has this intuition that actually this infinite series, in a way, converge. He doesn't speak in those terms, but they characterize infinite numbers. So things like 1 plus 2 plus 3 plus 4, or going on to infinity, or sums of squares of 2, 1 plus 2 plus 4 plus 8, and so on. And now we got to the first quotation here, where he says, now it is possible that an infinite, I left this in Latin, aggregatio, because it took quite a bit of work to be sure about what this word really meant, but you can take it on faith that it means summation in this context. Aggregatio can also mean other things, but in this particular context, we can take it to be summation. So that an infinite aggregatio of numbers tends to an infinite aggregatio in every numerical ratio and in every non-numerical ratio. And some infinities are more than others, and other less than others. Thus, the aggregatio of all numbers, both odd and even, is infinite, and it is greater than the aggregatio of all the even numbers, even though this too is infinite, for it exceeds it by the aggregatio of all the odd numbers. Now, there's a lot going on here that will need to be unpacked. I'm not going to do that because my focus will, in fact, be on another part of Grosseteste. But in my book on infinity in the early 13th century, I spend a lot of time articulating exactly what is going here. This is the book, The Wilderness of the Infinite. So, in which, as I said, I devote a great deal of attention to these passages on life. But here the focus is on the commentary on the physics, where Grosseteste defends, alongside these proposals about infinite numbers obtained by infinite summation, also a form of part-whole thinking for infinite sets of geometrical points. So his starting point concerns issues of measurements and what is more basic in measurement. It starts with a very Aristotelian type of approach. It says time numbers motion. But what numbers time? And then he adds a measured body is numbered by a rational line, but what numbers the rational line itself? And in section 77, it plays with the following imagined scenario. It says, assume there is only a single solitary line, nothing else, abstracted from matter. How can you measure this line? And here is the citation. But when a line is numbered, the means whereby it is numbered is baffling. For let us suppose that there is a single solitary line, and let us imagine it to be abstracted from all matter. Now, it cannot be measured on the basis of another line or of anything else that is length, because there is no other dimension of longitude apart from the line itself. Right? By assumption, there is only a single solitary line, so we don't have something else with which to perform the measurement. Nor can it be measured on the basis of itself. For how will one know on the basis of the line itself how long or how short that is? For instance, how could one know about a one-cubit line merely on the basis of the line itself that it is a one-cubit line? If one were to say that a line itself could be measured on the basis of some aliquot part of the line, how will one know that the size of the aliquot part? Sorry. Is me? Yeah, let me turn this off. This is Grosseteste complaining about how I interpreted the text. And it would have probably good reasons to be suspicious. Sorry about this. I turned off one, but not the other. And in section 78, Grosseteste repeats the same thought experiment, this time for time and motion. Start thinking about the solitary motion, how could it be measured, and he claims these are very difficult questions and the intellect can scarcely attain to them. And the answer he provides brings us back to infinite numbers. And he says, nevertheless, it is my opinion that, as we stated elsewhere, one infinite number can be related to another infinite number in every proportion, numerical and non-numerical. For there is some infinite number which is double in relation to another infinite number, and there is some which is triple, and so with all the other species of proportion. I cannot say how innovative this passage is. We have no one before Grosseteste who postulates the existence of infinite numbers in this kind of arithmetical context. If we want to do as it were, archaeology. Yes, there is some stuff about the Pythagoreans and Plato postulating some kind of infinite numbers, but it's all very metaphysical and very vague. This time, with Grosseteste, we reach a level where Grosseteste thinks that not only you can postulate infinite numbers, he has a theory how to generate them, which is the one that comes out of online. But also is telling us that there is a whole arithmetic here to be developed. And when he says that infinite numbers can be related to one another in every numerical ratio, what that means is that you can have infinite numbers that stand to each other as 3:4, 5:7, 1:2. So there is an infinite number which is double, another one which is half of another one, and so on. But even in every non-numerical proportion, meaning that two infinite numbers can stand in the ratio of the side and the diagonal of a square, for instance, a square root of 2:1, we would say. And there is also, I keep quoting from the commentary on the physics, and there is also some infinite number which is related to another infinite number as the diameter is to the side, as has been proven elsewhere. This is a reference to on light. And again, I make so bold as to say that every infinite number is finite to God himself, of whose wisdom there is no number. Even more than the binary, i.e. the number 2, is finite to me. To him, the infinite number comprised of all even numbers and is finite, and so too the infinite number comprised of all the odd numbers. And so too all the infinite numbers which can be divided infinite times over. I think he's thinking here of multiples of 5, multiples of 6, and so on. For just as things which are truly finite in themselves are infinite to us, so those which are truly infinite in themselves are finite to him. That's an interesting quote, somewhat passing. What exactly does he mean about, this finite to him? I think that basically he's emphasizing that God's view of this infinite number is to be compared or as being even more direct than the one we have about the finite numbers, that he has such a control on this infinity that he understands the infinite numbers better than we understand even the finite. So that's kind of, I think, what the essence is. And right, this is something I just said. And let's read some more of this passage. I don't think it's useless because, as I said, none of this has been translated. So unless you read Grosseteste, you might not have seen it. So, moreover, he created everything by number, weight, and measure, and is the first and most accurate measure. By infinite numbers, which are finite to him, he measured the lines which he created. By some infinite number, which is fixed and finite to him, he measured the number, the one-cubit line, and by an infinite number twice that size, he measured the two-cubit line. And by an infinite number half that size, he measured the half-cubit line. And there is a single infinite number comprised of the points in all one-cubit lines, by which he most accurately and most finitely measures all other one-cubit lines. But this way of measuring with infinite numbers is not available to men whose intellect is limited. So first of all, I love the metaphor of the absolute measure. It goes along with the other metaphors we have, like God, the geometer, and so on. In this case, is the mensurator. Also, notice that what is going on here is that numbers are used to measure geometrical entities, or at least they're being used to measure the number of points in geometrical entities like finite segments. Now, if you think about the relationship between arithmetic and geometry in the Greek world, apart from a period of Pythagorean control over such issues, we know that geometry became the dominant discipline, and in fact, in Euclid, for instance, we have that arithmetic is done by using geometrical technique. We represent numbers by line segments. I think we need to read these passages in Grosseteste as a comeback of a Pythagorean intuition. In other words, where numbers are becoming, again, primary, more fundamental than geometrical entities. And they are exactly what give the possibilities, the possibility for God to give absolute measures to these geometrical entities, right? So the problem that Grosseteste has is, well, normally when we do measuring, we have to fix conventionally a unit of measurement, right? It used to be the meter in Paris. Now they do things with atomic clocks, but right, you had to have something against which you would then conventionally measure everything else. And the thought experiment that Grosseteste invited us to follow was, well, suppose there is only the meter in Paris. How do you know how long that is? And his answer is, well, God knows, because God can measure exactly the number of points in that segment. And here is an important thing that we need to keep in mind when it comes to trying to mathematize what Grosseteste is saying. He's saying that every one-cubit line has got exactly the same number of points. In other words, what we call in contemporary mathematics translation invariance. If I have a one-cubit line here and another one down there, it's going to have exactly the same number of points. And so that although Grosseteste is starting from reflections that have to do with part-whole containment, right? The original one I gave you, take a segment which is 2 inches long, bisect it, look at the F, 1 inch long, twice as many points in the longer one in the shorter one. That's a part-whole type of reasoning. That part-whole type reasoning is certainly something that you want to preserve in the spirit of Grosseteste, but it would not allow you to, for instance, say that a 1 inch segment down there is has exactly the same number of points as a 1 inch segment here. So you need this intuition, which is stated very clearly in Grosseteste. Okay, so one final quotation from section 81. Well, then, what is the first means whereby the first already measured line is measured and numbered? I think this takes place by the means of the infinite number, finite nevertheless to the measurer, which comprises of the point, which is comprised of the points in that line. This number of points is not in any larger or smaller line. In every larger line, the infinite number of points is larger, and in every smaller line, it is smaller. This is the covariation I've been telling you about. If you take a segment which has length smaller than another segment, the number of points in that segment is going to be smaller than the larger one. So you have this way of, on the one hand, looking at measures. What we normally do with real numbers, right? We measure a segment, and so these different measures go together with different infinities of points. Now, the same thought, I'm not going to talk about William of Auvergne, but I want to give you at least one quote from the Universo. It's found in William of Auvergne, a contemporary of Grosseteste. In fact, this is a mystery for people who love this area of medieval philosophy. Apparently, they were friends, but we have no real smoking gun showing that they ever met. And neither one cites the other. And yet, there seems to be, enough evidence that somehow they went around the same circles, and maybe Grosseteste studied in Paris. It's all a bit of a mystery. I know some of these things through Cecilia Panti, who's a great expert on Grosseteste. Anyway, here is a typical passage in William, who's a very abrasive writer. He's very, kind of feisty in his style. So you should not be disturbed either by the error of certain feeble men who have failed to recognize or being able to recognize that it is possible for something to be beyond infinity or greater than infinity, for it does not escape even children's minds that the infinity of the points in any whole line is greater than the points in half the line, since the latter is a part while the former is a whole. So you see here this part-whole reasoning playing a huge role as it did in Grosseteste. And it is the same way with the relation of the half to the fourth and the fourth to the eighth and so on to infinity. Now, just to give you a sense of the difference, though, between William and Grosseteste, and why Grosseteste is so incredibly revolutionary in ways William is not, William is entertaining and countenancing the actual infinite, okay? But he is against the idea that there are infinite numbers. So he has a whole section of the University where he argues that there cannot be infinite numbers. So he has infinite collections, but not into measures in weight. By contrast, Grosseteste, as I said, took this very original step in the history of philosophy and mathematics that no one had taken before him. All right, now, before I get into the challenge, let me at least anticipate that I will come back to this challenge from a contemporary point of view. And I'm going to say that, to me, the amazing thing about this challenge is that it anticipates the Bolzano and Cantor debate by about 500 years. So let's just look at the challenge now. We'll say something more about it mathematically. So Richard Fishacre was the first Dominican friar to lecture at Oxford. He was also the author of the earliest commentary on the sentences of Peter Lombard that were delivered at Oxford around 1245. And in his commentary, Fishacre emphasizes what he calls the elongatio, this infinite distance between God and finite creatures. And it is while discussing the question of how a rational creature with only finite power can have a view of an infinite object like God, and this brings us back to what I said at the beginning about the theological context of some of this stuff. Fishacre develops a novel conception of God's infinity. He introduces the topic in the first book, Second Distinction, and the summary of that chapter reads, here let us raise a question about the vision of God in the fatherland, so in heaven. To this end, the question is firstly raised whether God is infinite, secondly, in how many ways he can be said to be infinite, thirdly, and this is the most important for us, how infinity or numerosity and supreme simplicity are reconcilable with one another. What kind of a problem is he addressing? God is simple, but he knows infinitely many truths, for instance. How can you reconcile his simplicity with his infinite knowledge, where the numerosity of his knowledge would be one example of such a thing. And then fourthly, how a rational creature with only finite ability is capable of that infinity. Now, it is in the section on how simplicity and infinite numerosity can be compatible that leads to a connection to the topic of mathematical infinity. And in question 3, the discussion concerns whether numerosity and simplicity are compatible. And after presenting a number of arguments against the compatibility of simplicity and numerosity, Fishacre argues, by offering 9 different arguments in favor, that simplicity is in fact compatible with numerosity. And we get to areas pertinent to mathematics only with the 5th and the 6th arguments. So this would be the ratio geometrica. Fishacre gives an example that will be repeated endlessly in the successive literature and in some variations. Okay, first I'm going to read you the passage. It's a little bit unclear, but then the next slide is going to make clear what the mathematical example is for. So likewise, the approach to the simple happens without diminution of numerosity, as is plain from 2 bases subtended to the same angle. for the smaller of these bases, approaches the simplicity of the angular point. And yet, it has lost nothing of the numerosity of its points. On the contrary, individual points in the smaller base correspond to individual points in the larger base. This is proven by a geometrical proof. For if two lines are drawn out from diverse points in the larger base to the angular point, they will pass through diverse points, albeit less distant ones, in the smaller base. Therefore, the numerosity of the largest line is equal to or not greater than the numerosity of the smallest and almost punctual line. And thus the simplest and the less simple are equal to one another in numerosity. Therefore, the absolutely simple and the numerous are not repugnant to one another. So, the example is what we give our students when we're teaching them Cantor's theory of sets and why two arbitrary segments of finite length have exactly the same number of points. Here it goes. Take any triangle like the one displayed up there. We have a vertex C, we have a basis B, and now consider any intermediate line parallel to the basis, let's call it A. If you start drawing from the vertex C, a point, a straight line to the base B, you will have an arbitrary point X. That arbitrary point X automatically also corresponds to a point Y in the smaller base. This is a one-to-one correspondence between points in the two different segments. And it's, as I said, it's exactly what we give our students when we're teaching them, why segments, have exactly the same number of finite segments, have exactly the same number of points from the Cantorian point of view. We give them this argument. And now what Fishacre does is to say, look, there is a decrease in simplicity as you go, there is an increase in simplicity as you are moving from base B towards the vertex C, say, as you pass through intermediate lines. So A is more simple than line B. But now imagine continuing this process until you reach what he calls the punta line. In other words, the point C. Then that single point, which is absolutely simple because in Euclid, right, the point is that which has no parts, so it's simplicity in itself, will contain exactly the same number of points as any one of the finite line segments. That's the thought. Of course, we could object to this passage to the limit, but that is not what I'm going to do, in the sense that what is really important for me here is not so much the limit point when the line hits C, which is of course very important for Fishacre because he wants to say that absolute simplicity and numerosity can go together. But for what I need, I don't need the degenerate point. Right? I don't need the situation where the single straight line degenerates into a point. I just need the intermediate cases. The following passage, let me see if I skipped. The following passage draws the consequence of the one-to-one association just set up. Not only the line B has the same number of points, numerosities, of the extreme point in C, but C also has as many points as the entire machine of the world. I kept it actually translating this way, machina mundi, because then I needed this expression and something that goes on here to point at the fact that later Rufus is in fact drawing without acknowledging it on some of this work by Fishacre. But let me read the passage. Likewise, from the aforementioned argument, it is plain that a single point has as many points as does the largest line. Of course, we're dealing with the Aristotelian cosmos. It's finite. There's going to be a largest line in this cosmos. And so he's saying, even the largest line has exactly the same number of points as any as a single point. After all, the lines that proceed from the larger base and terminate at the angular point have that very point at their extremity. And if one of the lines is removed and then repositions, it terminates at the point where it previously did. And the same applies to each individual line. Therefore, that point is equal in numerosity to that line, and consequently to some surface and to some body. In fact, there are as many points in a point as there are in the whole machine of the world. And since any point in the machine of the world, from any point in the machine of the world, a line can be drawn to this point in accordance to that point, a straight line can be drawn from point to point. Therefore, a point, although it is simple, still does not lack infinite numerosity. Therefore, I've proven the proposition. As I said, one could object to the limit point, but not to the argument that has to do with two arbitrary finite lines. I think that's a pretty solid argument, unless you are someone who believes that there are only finitely many points in segments, but then you're in real trouble if you believe that. So let's just not get there. But there were people in the Middle Ages who believed that particular proposition. Now, one should not underestimate the force of this argument by Fishacre, whose net effect is to undermine all the approaches to sizes of the infinity that claim that the length of segments covaries with the numerosities of points. And that was Grosseteste's point of view. The one-to-one association between segments of different lengths shows that any two segments of different lengths have exactly the same numerosity of points. In my book, I show that Richard Rufus took up the challenge of defending Grosseteste's intuition, and that out of these debates, which are present in many English commentaries on the physics in the period 1250 to 1270, extensively studied by Cecilia Trifogli, a position emerged which was greatly to influence 14th century thinkers such as Rem, Buridan, and eventually Galileo. And this is another important historiographical point. The great historians of infinity, Annalisa Meyer, John Murdoch, Pierre Duhem, they focused on the 14th century. Surely an exciting century, especially for natural philosophy, but somehow they almost completely ignored the 13th century. And so, for instance, John Murdoch suggests that this position that we're going to be looking at when we discuss Galileo, and that is typical of 14th century Paris, i.e. the position that when it comes to infinity, you should not try to apply relationships of size to infinite collections, so that you cannot apply less than, equal to, or greater than. They thought that this was a Parisian 14th century creation. By contrast, in this book, I show that it was already there in the 1250s in Britain with various commentators on the physics. Okay, I don't want to pursue now this particular line because I want to get out of the Middle Ages and move on, but at least one quote that goes in this direction to show that, in fact, this position I'm talking about is foreshadowed already in the 1250s and 60s. So this is from William of Clifford, where William says, there is not the same number of points in a greater as in a lesser line, nor are there more points in one than in other, nor are there fewer, because all of these are differences that are characteristic of finite and terminated quantity. In other words, this is what I call the deflationary talk about infinity. It's a deflationary talk because at best you end up saying they're all infinite. They all have an infinite number of points, but you can't say that they're even equal or less than another in terms of number of points or greater than. And in fact, here is Galileo from the very famous passage in the Two New Sciences, wrapping up the discussion on paradoxes of infinity, where after having discussed how is it possible that the natural numbers are in Are they greater than the square numbers, or are they the same? And of course, we're pulled in two different directions because we have a part-whole intuition, and we have also this one-to-one correspondence intuition, which we have seen already emerging in that debate between Grosseteste and Fishacre. And we are going to encounter it here. So Sagredo says, what then must one conclude under the circumstances? And Salviati replies, well, so far as I can see, we can only infer that the totality of all numbers is infinite, that the number of the squares is infinite, and that the number of the roots is infinite. Neither is the number of squares less than the totality of all numbers, nor the latter greater than the former, and finally, the attributes equal, greater, and less are not applicable to infinite, but only to finite quantities. And now for the line segments. When therefore Simplicio introduces several lines of different lengths and asks me, how is it possible that the longer ones do not contain more points than the shorter? I answer him that one line does not contain more or less or just as many points as another, but that each line contains an infinite number. Okay, so this is what I call, as I said, the deflationary attitude. Just don't try to extend relationships of size from the finite to the infinite, because it's almost a categorical mistake. Those relations only belong to the finite. All right, now we jump to Bolzano and Cantor. Because these two intuitions have been pursuing since Grosseteste and Fishacre are exactly the ones that are more familiar to philosophers of mathematics nowadays. Bolzano, and by the way, and neither Bolzano nor Cantor are deflationary about infinity. Both of them want theories of infinity where infinite sets get measures. Bolzano calls this measure field height. And Cantor will call it Mächtigkeit for power, and then it will become the cardinalities that we know from set theory. Now, what does Cantor do? Before I get to Bolzano, Cantor uses one-to-one correspondence to measure sets of the size of sets. So, quite famously, all sets of natural numbers which are infinite in Cantor have exactly the same size. They have size which is called Aleph0, which is the size of the natural numbers. Why? Well, for instance, take the even numbers. The even numbers can be put in one-to-one correspondence with the natural numbers. All I have to do is to list the natural numbers, and then for each natural number, I take the double, right? So to 0, I associate 0, to 1, 2, to 2, 4. And so this one-to-one correspondence, which is very natural for us, right? It's like, how do you know there are the same number of forks and knives in a well-set table? Because to each knife, there is exactly one fork that sits next to it, and so on. So that's the intuition. And Cantor does a wonderful job of setting up a mathematical theory of great power using this intuition. But 30 years before Cantor, Bolzano is also struggling to obtain a theory of infinite sets. And these infinite sets have to be measured. And he wants a measure for these infinite sets. And the amazing thing about Bolzano, 30 years before Cantor, is to say, and this is from the Paradoxes of the Infinite in section 20, he's saying, look, infinite sets have this very peculiar property. This is what we call reflexivity nowadays. You can take an infinite set and it can be put in one-to-one correspondence with a proper subset of itself. So for instance, right, take the natural numbers and you can put them in one-to-one correspondence with the even numbers. Every infinite set has in fact that property. And it says, 30 years before Cantor, says, but don't make the mistake of thinking that one-to-one correspondence is going to give you a criterion for size. So he's looking, why? Because size, measured in that way, does not preserve part-whole relations. And so we see right now the other trend that insists on preserving part-whole relation and the attempt on the part of Bolzano to come up with a theory that in fact will have the infinite numbers he'd like to come up with correspond to part-whole relations. Unfortunately, it did not succeed. The mathematics for doing that was not there, and it was too difficult to bring that problem to solution at that time. And this, I think, and we can talk this in the question and answer period, had incredible consequences both for philosophy and for the historiographical issues related to infinity. Okay, now we move to contemporary stuff. So in abstraction and infinity, I actually explored how the recent theory of numerosities, which is due to a number of Italian analysts working in non-standard analysis, allows one to extend counting from finite to infinite sets in such a way to preserve, in contrast to Cantor's notion of cardinality, the part-whole principle as it had been propounded exactly by Bolzano. What is this part-whole principle? Let's try to make it a little bit more mathematically significant. So if A is strictly included, where strictly included is just set theoretical inclusion. If A is strictly included in B, what we would like is that the size or the numerosity of A should be strictly less than the numerosity of B. In Cantor's assignment of cardinalities to infinite sets, this principle does not hold, since the natural numbers and the even numbers, which are contained in the natural numbers, have the same cardinality. So cardinality as it were, as a notion of measurement of size for infinite numbers flouts the part-whole principle. So our problem at this moment then becomes to see whether the desiderata concerning the number of points in segments that we saw already with Grosseteste can be vindicated using numerosity theory. Now, the study of the theory of numerosities and its relation to measure theory goes back to no more than about 10 years ago. And I want to summarize for you the mathematical results, but I want to do it in such a way that I don't even, that the slides are more technical than I want my, as it were, presentation to be. And I want to tell you, first of all, something about measure theory. Measure theory is a classical area of mathematical analysis, is the theory over which we do integration in a proper way. But what measure theory does at the very basic level is to assign real numbers to subsets of the real one. In particular, we might be interested in measuring the length of an interval in the real one. The interval points from 0 to 1 or from 0 to 5, and so on. In fact, what the notion of measure aims to capture is the intuitive notion of length, and then it extends it by means of property that must be satisfied by the notion of measure. There is an important point here philosophically that is taking place in my presentation. When we go back, of course, to Grosseteste, Grosseteste was talking about line segments in a purely geometrical context, right? There is no arithmetization of the lines there. It's just geometrical objects. When we do this kind of work and when we try to make it precise through mathematical means, of course, we take for granted that the plane and the line segments and so on have already been coordinatized. So we're working with a kind of analytic geometrical setup. But that doesn't really make, as it were, a great difference with respect to what we're after. Okay. So Lebesgue in 1902, in his famous dissertation, asked whether there could be a function mu such that for all subsets of real numbers, A and B, bounded, so these are not infinite sets in the sense of not having a bound, they are all bounded in some way, one could have, one could satisfy four properties. One is totality. One would like for every bounded subset A that there is a real number associated to that subset greater than or equal to 0. Non-triviality, you don't want everything to have measure 0. You want something at least to have something measure greater than 0. Translation invariance is key already for the things I've told you. Translation invariance means that if you are giving a measure to the interval 0, 1, and you're looking at the interval 6, 7, because one can be shifted onto the other by adding exactly the same constant to all the points, you want the measure of those two to be the same. And we saw that Grosseteste was really explicit about that principle. And finally, we have countable additivity. I don't really need to get into it. Here, the idea is simply that if you have two measurable sets and you look at their union, so you take, for instance, the point in the interval 0, 1, and you add, say theoretically, you do the union with the interval 6, 7, you get these points in 0, 1, and 6, 7. The measure of the entire collection is simply the sum of the two measures. So in fact, in that case, they will get measure 2, 1 from the first interval and 1 from the second one. Now, Lebesgue introduced a class of sets called the measurable subsets and solved the measure problem for that restricted class of bounded subset of the real numbers. In fact, Vitali in 1905 proved that there are bounded subsets of the real line which are not measurable. And so in full generality, if you assume the axiom of choice for those of you who are into foundations, in full generality, the Lebesgue problem is not solved. You cannot have all the properties I listed before satisfied at once. Usually, what one does is to give up totality. One says, okay, we can't measure all these bounded subsets, but we can measure, a class of such, and those are called the measurable subsets, which Lebesgue had already introduced. But they contain all the things of interest. I mean, to really find a non-measurable subset, you have to work very hard. It's not anything that will naturally arise in your work. This I've already said, ordinary finite intervals. So this is called, this Lebesgue measure is this function that does this measurement for us. For ordinary intervals, you get exactly what you expect, where, we take intervals, like 0, 1 or 2, 3, they have measure 1, or if I take 2 to 4, in the real numbers that gets length 2. So the measure for the Lebesgue measure will be 4, and so on. So the point here is that all of the kind of finite segments that Grosseteste would have been worrying about are all contained in the Lebesgue measurable sets. Because he wasn't talking about anything fancy. They were just line segments, and then you might look even at, summing to line segments or things like that. Okay, now, at this point, and I'm almost done, we get to the really new stuff. Remember what our problem was. Our problem was, can we put together this notion of measure, like, this is 1 inch long, this is 2 inches long, and so on, and the notion of numerosity, where we assign a number of points to the finite segments, and we get this correlation or covariation, as I've been calling it, between the two. Grosseteste said, yes, God does that, in fact, with this ability to use infinite numbers. The challenge by Fishacre was, no, you're crazy. Here is the one-to-one correspondence showing that you can't get that kind of covariation. So what's the situation with Cantor? And remember, Cantor is the only theory of infinity that managed to assert itself because the alternative, the Bolzanian one, did not have enough mathematical coherence to to receive attention. Well, Cantor sides with Fishacre. I mean, of course, he doesn't know Fishacre, but that theoretically speaking, he says, "Oh, that's a crazy idea." Again, all of those segments have an uncountable number of points, so the same cardinality as the real numbers, and so it doesn't matter, whether they're 2 inches long, 1 inch long. The number of points is exactly the same because the cardinality is the cardinality of the real numbers. So the challenge here, mathematically speaking, is to say, can we find a mathematical theory that allows us to count points in such a way and to relate it to measure in such a way that we regain Grosseteste's desiderata, so to speak? And the answer is yes, we can do it. And it comes exactly from this theory of numerosities. So first of all, to tell you something about the theory of numerosities. The theory of numerosities is a theory that has as its principal goal to find a way of measuring the size, but this time called numerosity, exactly to distinguish it from the Cantorian cardinalities, the size of sets in such a way that, this is the key, that the part-whole principle is always preserved. To see how radical this is, imagine if I have the set of natural numbers. If I have such a function, like a numerosity function that preserves part-whole, if I pluck the number 17 out of the natural number, the size, the numerosity of what remains is strictly less than the original one. This is an incredibly fine way of measuring the size of things. See, the Cantorian relation of equivalence puts in the same bag a lot of stuff, right? All the even numbers, the prime numbers, the odd numbers, they all have the same size. They're all infinite, countably infinite. Whereas the theory of numerosities is taking a different criterion of measuring, so that even if I take only 1 point away, this is going to change the numerosity. But now you can also see the challenge with respect to putting measure and numerosity together. So in fact, before I get to the slide, let me just put it concretely. You know that in when you measure the length of these intervals of real numbers, if you take the closed interval 0, 1, it doesn't really matter whether 0 is also there. You could take the half-open interval. 0 is not there, but 1 is there, or vice versa. You can have the 0 and then keep it open on the right without the 1. The Lebesgue measure of all those sets, it's exactly the same. Okay, they all have length 1. But if we are dealing with the theory of numerosity, if I pluck away even one single of those elements, the numerosity is going to change. So we need to do something really clever in order to have this covariation between numerosities and measure, exactly because it must be, the solution must be such that it will not suffer from the removal of 1 point or another. So the two key definitions, and I'm going to close with this. First of all, you need a definition of a finitely additive measure. That's a triple with a set W, a set of subsets of W, and finally the measure mu. And these things are what? Well, W is simply a non-empty set. And then I is a non-empty algebra of subsets of W. An algebra simply is something that for any two subsets in I, the union is in there and the relative complement. And then finite additivity simply says that if I have this measure, when I apply it to the union of two sets which are disjoint, well, then the measure of the union is simply the sum of the individual measures. One important thing about this type of measure we're going to look at is that a measure mu is non-atomic if all finite sets have measure 0. And this is typical, in fact, of real analysis. For instance, think about, when we do probability, we're dealing with measures in that sense. If I throw a dart at a real line, and we ask, what is the probability that a specific point is hit? And the answer is 0. Now, again, that might surprise you if you're not ruined by contemporary intuitions in mathematics, because you might want to say, wait, after all, after I throw the dart, one got hit, right? And so how could the probability be 0? So this distinction between possibility and probability is a key one in contemporary approaches to mathematics. So what we want to do now is to put together this notion of finitely additive measure with the notion of elementary numerosity, because those are the two notions that have to contribute to the covariation. Now, what is an elementary numerosity? Again, one starts from a set W and then tries to define a function U from the entire power set of W into what? Okay, and this requires a little bit more mathematics than I'm going to be able to get into, but fundamentally, what you do is to work with a field, like the real numbers are a field, but the field we need to use are fields that have infinitely large elements after all the ordinary real numbers. And those infinitely large elements will, in fact, turn out to be useful for giving us the infinite numerosities we need. But in general, then, this elementary numerosity takes a subset of W and assigns it an infinite number, just like Grosseteste was assigning infinite numbers to line segments. And how do we do it? Well, first of all, this is a notion of numerosities. We are counting them. So the first thing you want is that all the single ones of W, the single elements, have numerosity 1. It's just a generalization of our normal counting. Again, we have finite additivity. What is the numerosity of two disjoint sets that get put together? Well, it's the number of the things in A plus the number of the things in B. And finally, as a consequence of these properties, you get that the only thing that has numerosity 0 is the empty set. And of course, the key thing we want is that if A is strictly included in B, then the numerosity of B must be strictly less than the numerosity of A, must be strictly less than the numerosity of B. To conclude, these requests are requests for a special theory of counting of numerosities that we need. Cantor also gives us a theory of numerosity in terms of cardinalities. Here's the interesting thing. On the finite, so when we're looking at finite subsets of an arbitrary set, numerosity theory and Cantorian theory do not disagree. They give us exactly the same results. The disagreement takes place once we go to infinity. Again, implementing what Galileo and the people before Galileo had already seen, that two different intuitions about measuring the sizes of infinity are at play, but now we know that they can be given a formal mathematical implementation. So, our goal, as I said, is to see whether Grosseteste intuition on the number of points and segments could be implemented. So we need to see whether we can put together a Lebesgue measure and these new notions of numerosity in such a way that we have this correlation. And one simple-minded way to do that would be to write down something like that. The measure of A, and we could take Lebesgue measure, equals the measure of A prime if and only if the numerosity of A equals the numerosity of A prime. And notice, the terms flanking the left-hand side, mu A prime, those are real numbers. They are measures in the sense in which we understand them as real numbers. The numerosities on the right-hand side are infinite numbers, which are taken from these extensions, right, of the field of the real numbers that I was telling you about. And the answer then to this request is going to be positive if we cleverly choose the algebra of intervals to be the one with the closed intervals that are closed on the left and open on the right. That's a minor, as it were, technical detail that is going to allow us to do exactly what we want. So to conclude then, let me just read this theorem. So suppose we have the Lebesgue measure over the real numbers, meaning we have a triple with the real numbers, the Lebesgue measurable subsets, and the Lebesgue measure over the real numbers. Then, in fact, there exists an elementary numerosity nu from the power set of the real numbers into a non-Archimedean field F. That's what gives us the infinite numbers, such that, for instance, we have that the numerosities of two intervals that are congruent, it's exactly the same. And remember this, that's the translation invariance that we have been talking about. So in the end, after all the work is done, we get exactly what we wanted, that we find, given the Lebesgue measure, we find a non-Archimedean field F such that we can have the covariation that was required to make sense of what Grosseteste was asking. Summarizing, the last theorem shows that there are elementary numerosities compatible with Lebesgue measure on a significant collection of subsets of the real line, which includes all the sets that were relevant to our historical investigation. Defending part whole, so that the length of segments covary with the numerosity of the points, as Grosseteste and William of Auvergne did, turns out not to have been such a foolish idea after all. Thank you very much.
We don't have much time, but still we have some time for questions. Pedro?